another thing that solutions can do is called osmosis, which is the flow of solvent from a solution of low concentration into a solution of high concentration. Often when we're talking about osmosis, these solutions are separated by a semi-permeable membrane, which allows solvent to flow through it, but not solute. An example of a semi-permeable membrane is a cell membrane. So you'll run across osmosis in biology as well. Now, the osmotic pressure is the amount of pressure needed to keep osmotic flow from taking place. We use a capital pi for osmotic pressure, and it is directly proportional to the molarity of the solute particles. So the osmotic pressure is the molarity of the solution times R, the gas constant, 0.08206, times your temperature. Here's a picture of osmosis for you if you're struggling with picturing it. So if we have a solution over here and pure water over here, the water is going to flow faster towards the solution than it will back to the pure water. And so overall, once we're at equilibrium, the water level on the solution side will rise, and we'll have this extra pressure on the solution side compared to the pure solvent side, and that pressure of the excess fluid is the osmotic pressure of the solution. That's how you would measure it in a lab. So here's an example to work through. What is the molar mass of a protein if 5.87 milligrams per 10 milliliters gives an osmotic pressure of 2.45 torr at 25 degrees Celsius? And remember, our osmotic pressure is the molarity times the gas constant times the temperature, and R is 0.08206 liters atmospheres ATM over Kelvin times moles. We're given an osmotic pressure of 2.45 torr, which we want to convert into atmospheres, so our R value works. There are 760 torr in 1 atmosphere. So our osmotic pressure in atmospheres is 3.223, or 224 really, times 10 to the minus 3 atmospheres. Then I can take my 3.224 times 10 to the minus 3 atmospheres, divide it by 0.08206 times 25 plus 273 is 298 Kelvin. And I get an answer of 1.318 times 10 to the minus 4 is my molarity. That is in 10 milliliters, so 0.010 liters times 1.318 times 10 to the minus 4 moles per liter gets me 1.318 times 10 to the minus 6 moles. And then from my question up here, I have 5.87 milligrams, so that's 5.87 times 10 to the minus 3 grams in that many moles. And if I do that math, I get 4.45 times 10 to the third grams per mole. One more practice, I would recommend pausing the video, making sure you can work this through on your own. Lysozyme is an enzyme used to cleave cell walls. A solution made by dissolving 0.0750 grams of lysozyme in 100 milliliters results in an osmotic pressure of 1.32 times 10 to the minus 3rd atmospheres at 25 degrees Celsius. Calculate the molar mass of lysozyme. So this is going to be very similar to the last question. where our osmotic pressure is the molarity times R times the temperature. My osmotic pressure is 1.32 times 10 to the minus third, and I can divide that by my R, 0.8206, times my temperature, 25 Celsius, is 298 Kelvin, to get my molarity, which is 5.3979 times 10 to the minus 5 moles per liter. Multiply by my liters, 100 milliliters is 0.1000 liters, which gets me 5.3979 times 10 to the minus 6 moles, and that is 0.0750 grams. So 0.0750 grams divided by my 5.3979 times 10 to the minus 6th moles gets me a molar mass of 1.39 times 10 to the 4th grams per mole.